So now when do you carry out SFRA test? So when transfer movements from manufacturing end to customer end, transformers may relocate at other places. So when we are shipping at a large transformers, as I told you in the beginning that on the road also transformer experience a lot of jerks, and as recorded it can be equivalent to as high as 60 Gs, which is a very strong vibration or the jerk, and under that movement the transformers within the tank, if it is not properly anchored or fixed inside the tank, and that may also reflect when we test the transformers on arrival. So nowadays for most large transformers, it is a practice, not mandatory but practice, to test the transformer after mounting on the trailer for transportation. So then we have a reference signature, because these transformers most of the times are transported without oil. So we carry out this test without oil. So we have a reference signature of the transformer geometry when loaded on the trailer and on arrival at site. Before we unload the transformer from the trailer, this test is performed again to ensure that during transport no movement of parts have taken place inside. So once we are assured that the transformer geometry is intact on arrival, then only we unload the transformers. So the test is performed before shipment from the manufacturer's work and on arrival at customer's end. When an abnormal event has happened, for instance an out-of-phase synchronization. Of course nowadays out-of-phase synchronization is very rare, but still sometimes the error do happen in connections, and most of the time this type of phenomena happens when the PT is connected in wrong polarity, and so when we are checking angle 0, if PT polarities are reversed, one of the PT is reversed, then the 360 degree what we are seeing, 0 or 360 degree what we are seeing on synchroscope is 180 degree. So we will inadvertently close the circuit breaker in phase opposition, and this will cause a major short circuit inside the transformers. So if this type of event has happened, then again we carry out the SFRA test and check whether transformer integrity is there or it has suffered some damage. When a long duration short circuit has occurred, now sometimes we think that long duration, how long is a long? But in electrical system, when we are talking about protections, we are talking of isolating faults within 100 to 200 or maybe 250 milliseconds. We are talking in terms of milliseconds and not in seconds. So, and if your protection coordination is not proper or DC is not available, and because of that the fault which is in a particular zone, that circuit breaker does not have a DC, or it is a stuck breaker conditions, and then we have to depend on the local backup breaker protection scheme. So if we face such a contingency in the field, that time the short circuit may continue maybe for 500 milliseconds or so, and that is considered as a long duration short circuit, and at that time we suspect that transformer may suffer some damage. Line protection operations followed by bushing failures. So sometimes we have a fault on the transmission line and the line trips, but then at the same time the bushing also suffers some failure and bushing blasting happens. So differential area protection, Bucos, PRD operations followed by line faults. So this is another conditions where you say there is a fault within the transformer with protection zone. So it trips on differential, transformer differential, and followed by a line fault. So if, of course, these type of conditions are very rare and it does not happen on a regular basis, but once in a blue moon type of thing, this can happen. Just to share my own experience, it was my first visit to a 400 kV substation after my joining job as a fresh engineer, way back in 1977. And I was there because CVT or product for which I was responsible was giving some problems, so I was there to investigate that. And the moment I entered the substation or control room, outside the substation on a 33 kV junctions, so a crow got trapped in the line, and because of that there was a crow fault on the 33 kV side. At the same time, the testing people were testing battery in the control room, and inadvertently that test engineer, he short-circuited the battery terminal and fuse blew up. So entire substation did not have a DC power, not at 33 kV, not at 132 kV, not at 220 kV, not at 400 kV. And fault was cleared in 4th zone from Sultanpur, some 400 kilometers away. At 400 kV circuit trip, and then this fault would isolate. But by the time it was a long duration and 30 kV CT had caught fire and there was a fire in the substation. So though long duration short circuits is more a theoretical concept, but it do happen once a while. So it is not something which is just an imagination. SFRA helps in decision making by performing the different tests and results may be compared with. So SFRA will help you arrive at a particular decisions comparing with the previous results. As I told you, nowadays when we ship the transformers, before dispatch we carry out SFRA taking as a reference signature, and then on arrival we check it again to ensure that the transformer travels safely throughout its journey. Comparing results between phases. So now in that particular case we deliberately take a reference signature and then compare, but sometimes you have very old transformers and you don't have a reference signature available. So then what you do is compare results between the phases. So in the same transformer, if you suspect the R phase has developed some problem, then you compare SFRA of R phase with Y and B and see that if there is any disturbance you are able to see on that phase. Or comparing results with the similar design assisted units. So you say the transformer suffered a major failure and all the 3 phases have suffered some damage, and you don't have any reference for that, then what we suggest is same manufacturer, similar design, you test the transformer, so that gives you a reference signature, and with that you can just compare whether the transformer which has suffered some fault has developed some permanent damage. So to identify the nature of problems, it is not only that there is a problem or not, but then what type of problem the transformer has suffered. We can find that out, and based on that we can decide whether it will have to go back to manufacturers for repair or it can be repaired at site. So this type of decision is possible with SFRA test. So, SFRA basics in a passive device, there are three basic components. Now, transformer is not an active device. It is definitely a passive device because it is a static device. There is no moving parts in transformers. So, it is a passive device and it has three basic components: resistors, capacitors and inductors. They each have a different response to an AC signal. As I explained you in the beginning, depending on the frequency, the impedance of L and C will change, and because they are all frequency dependent, and so it has a different response to an AC signal. The response is closely related to the geometry, both internal and in relations to the other components. So this is very important statement because I take a transformer winding per se. So transformer winding shown capacitance in the capacitance with reference to the tank, or if you take it between R and Y phase, then between the phases also there is an insulation, and because of between them also there can be a capacitance. So the relative position of the winding with reference to tank or with reference to another phase winding also can have an influence on capacitance or inductance measurements, and when we measure it, its response can reflect that. So this graph shows that now this red line in this graph is a resistor. So resistor is not dependent on frequency. So irrespective of frequency, its value will remain constant. So you see a straight line. Inductor, as I told you, the XL is 2 pi FL. So F increases, though L remains constant. Impedance XL increases, and this is represented here by a pink line. So this pink line shows the behavior of inductance. Capacitance, the impedance of capacitance can be calculated as 1 upon 2 pi FC. So as F increases, impedance decreases, and this is represented by a blue line here. So you now get a basic fundamentals that with reference to frequency, except for R, XL and XC will keep changing, and that can be calculated or that can be plotted in terms of a graph. So what we do is we have a V input, which is a, and we measure V output. So I inject transformer signal in the R phase of the transformer winding and measure output on the R phase of the on the LV side, and this V input and V output are measured at different frequencies, and the ratio of that is calculated and in logarithmic formats in terms of dBs, and that is equal to 20 log V output upon V input. So this mathematical equation gives us a particular transformer response at a given frequency, and that can be plotted in the graph. So it's like a two-port network. So we have a primary, that is Z11, secondary, which is Z22. You have between primary and secondary Z12, and we have primary and earth, or the windings and earth, that is Z21. So these impedances are calculated, checked, and then we see how it behaves. So this is the equipment through which we carry out this test. So here you can see we have a H1, there is a red lead attached to H1 bushings, and black lead which is attached to H0 bushings. Test lead ground should attach to stud or bolt at base of each bushings. So this is how we measure. On the high voltage side we inject the signal, on the low voltage side we check what is the output, and that input and output is given to the instrument, and then the instrument has a built-in algorithm so that it will calculate 20 log V output upon V input, and in terms of dB, and then it will plot in terms of graph. Transformer, now before we start this test, the transformer should be disconnected from the system. The reason for that is we do not want influence of any stack capacitance or any additional elements which has a capacitance or inductance value, because if those components are getting involved in the measurements, then the response will not be only of the transformer, but the response will be a combination of the total constructions. So it is recommended that transformer should be fully disconnected, and then only this test should be performed, so that you are checking geometry of transformer and transformer alone, and not having influence of any additional other component. Transformer should be in the normal service conditions. So when we say normal service condition, means fitted with bushings, conservators, and filled with oil, so that as if it is a normal service condition. Make connections as determined by winding configuration. Phases not under test are usually left floating. So we are not earthing those terminals, but we just leave them floating, so that it may not have its influence. If we try to earth it, then there will be some circulating current flowing, and then the whole impedance calculation, all other terminals should be left open and floating. Testing procedures. There are different standard test templates available for 2 windings, 3 windings, auto transformers, and shunt reactors. Before proceedings, actual measurements on transformer instrument and its cable must be calibrated, tested. The result shows along with the instrument the H0 defined response, size and configuration of the cable, testing cables. But this should be short-circuited, and on the dial you should say that the impedance of that is practically zero. Lead wire influence also should be utilized. It is advantageous to take responses from a single individual winding with different tap positions, that is maximum, minimum, and normal tap, which helps for future references. So if we are testing a transformer which has a tap changer, whether OLTC or off circuit, but then it is advisable that it should be tested at different tap also, preferably maximum, minimum, and normal. Maybe you can take 1 or 2 additional points in between, but these are the 3 extreme points for which the graph should be obtained. So it serves as a reference graph for future. Movements of tap must be noted during testing, especially when a reversing switch is present. Now, I'm sure you people are aware that when we have a tap changer, we achieve the change in turns ratio by changing direction of current. So tap winding is only one, but the same winding is used as to add the turns or subtract the turns. So that we achieve by reversing the current directions. So if I add turns in the same directions, then the number of turns on the primary side will increase. So turns ratio will increase. If I connect this at the same time in the reverse direction, then those many turns will get reduced, and so turns ratio will also reduce. So this is how we achieve. So direction of tap position must be clearly noted so that we don't make any mistakes in interpreting the results. Movement of taps must be noted during testing, especially when a reversing switch is present. So whenever we have to add or subtract, then we use the reversing switch, and that is how we change the direction of the current. Earthing points where the earth leads needs to be connected must be properly cleaned. The conditions, that is grounding, oil level, tap position, etc. should be same for factory and field test. The reason is because this is more a comparative test. So we have to compare it in identical conditions. The smallest possible section of a transformer winding should each be tested separately. Open circuit tests are performed on a winding with all other connections floating and disconnected. Short circuit tests are performed on a HV winding by shorting together the LV connections without grounding. The neutral is not included in the shorting process. So we check the open circuit impedance, we check short circuit impedance, and based on that we do some calculations. So this circuit diagram, it shows the open circuit test. So here you can see on the LV side, this is an infinity impedance. So the current has to circulate in this area only. So this will be possible only through core. So at a low frequency, this will identify the problem in the core area. There is a short circuit. So since the LV side is short circuited, the impedance of the core is relatively higher. So core is not involved in the process, and then the winding is involved, and that's how you can see how it can identify the winding deficiencies. Open circuit response is dominated by core at low frequency. As with exciting currents, different magnetic paths lead to different responses. Typical outer versus central phase. So now here I would like to draw your attention that the outer phase, that is R and B, they are on the outer side of the core. So it has not a closed loop magnetic path on the other side. Whereas Y phase has a closed loop magnetic path both on R and B side, so that its behavior can be slightly different. Short circuit responses remove effect of core at low frequencies, as with leakage reactance. All three short circuit responses should be identical. Variation in the results may occur near 20 Hz due to variation in resistance elements of shorting leads, may indicate a need to check transformer with DC resistance test. Variation in inductive roll-off is due to variation in the winding impedance. Central phase may be slightly different. We expect all three phases to be within 3 dB. So this is a typical plot. So now how do we determine the fault inside the transformers? So we have identified that into 4 different regions. So the test is conducted from 20 Hz to 2 megahertz. This is a logarithmic scale. And zone 1 or region 1, we say it is less than 10 kilohertz. So when I am supplying a signal below 10 kilohertz, the whatever distortion if I see in this region, then it shows that there is a deformation, open circuits, shorted turns, and residual magnetism. So if your core is having a residual magnetism, it may also show you a distortion in this region. In region 2 is from 10 kilohertz to 150 kilohertz. The bulk winding movement related to earth and others, clamping structures. So if you see a distortion in the region of 10 to 150 kilohertz, you can say that there is some problem in the winding, or the winding is deformed, or relative movement is there in the winding, or a clamping structure is changed. So somewhere a movement has happened in the winding. Region 3 is 150 kilohertz to 400 kilohertz. Deformation within the main and tap winding. So if we find a distortion between 150 kilohertz to 400 kilohertz, then we say is a deformation within the main and tap winding. And if we see distortion between 400 kilohertz to 2 megahertz, it is more a movement of the main and tap winding leads. So tap winding leads have also suffered some distortion. This will be reflected in this region. So we will be taking the case studies to explain how these regions are, how the problem is seen in the region, and then what exactly was the fault identified in the transformers. See, here we are seeing a typical good short circuit results. Now here you can see the roll-off has changed. And then when we ask customer that did you do any winding resistance measurements on these transformers, they say yes. Just previous week they had done winding resistance measurements. Now winding resistance measurements, we are doing injecting 100 ampere DC current. So DC test on the transformer should be done the last, because if you do a DC test in the beginning, then there are chances that some permanent magnetism may remain, that will be residual magnetism in the core because of the DC, and unless the demagnetization is done, some of the test results may be erroneous. So these transformers, after we demagnetize, it came this blue line, it shows which is a normal. So earlier it shifted by 7.5 dB, which was an indication that the core has some residual magnetism. This is where I was saying, it was said that the direction of the tap should be clearly noted, because if the direction changes, your graph can show you a distortion. So noting down the direction is very, very important. Here you can see it is H0 to H1, and this graph is H1 to H0. So if you are not conscious of the directions, you may have some erroneous results, and then it can lead to wrong conclusions. Now, as I told you, this test is all about RLC. So if the tap changes or the tap direction changes, now tap 3 and tap 11 physically should be the same, but then the winding is in the reverse directions. So that is where you see is parallelly shifted. The red line and blue line are displaced by few dBs, but that is only because of the change in direction. So inductance capacitance value changes. This is if you have the changeover switch, and if you don't note it, then this can happen. You can see the distortion is mainly from 10 kilohertz up to 2 megahertz or 1.5 2 megahertz because of the reversal of directions. Now, as I told you that nowadays there is a practice that the large transformers before shipment and after loading on the trailer we carry out SFRA, because that time it is without oil, and when it is arrived at site, obviously you cannot feel oil in that, so you will also perform tests without oil. So a reference signature of the transformer is taken without oil, and after you install on the plinth and fill up oil, obviously you want to have a reference signature for fully oil filled transformers. So here you can see with oil and without oil. Of course the capacitance value will change because oil as a dielectric will have a relative epsilon 0 or higher values compared to air, and so you see, otherwise you will see that both the graphs have moved parallel after with some points. So this shows that with oil and without oil, the SFRA plot may differ by few dBs or frequency bandwidth in right way or left side. This is, you can see original SFRA plot, and then the lead suffered some problem or short circuit with ground, and then when you plotted the SFRA, you find that it shows a distortion here, this yellow line, and with that you can identify that yes, something has gone wrong with the lead of the transformers. We say that up to 10 kilohertz, you will see the change in core behavior or magnetization in the core, and this plot is typically explaining you this green line and blue line. It shows that previously the core was having a residual magnetism, which is done plotted by blue line, and you can very clearly observe that after 100 kilohertz or even up to 50-60 kilohertz, this plot is almost merged. So these up to 10 to 20 kilohertz, this is predominantly reflecting the core area, and you can see here the behavior of the core, residual magnetism versus unknown magnetized core. So interpretation of the results, each design has a characteristic responses. Responses from sister units should be identical.